Hi, I'm Arsham, and this series of videos about computer science and game development are sponsored by Kitacode. I've started taking a course called CS50 made by Harvard, which gives you all the knowledge you need for computer science and game development. And this series of videos are summarized versions of that course. Feel free to check it out for yourself. Now on to the video. In today's video, we're going to talk about binary and other systems that computers can use to represent data. In the previous video, I went over what is computer science. If you haven't watched that one, go ahead and watch it, because it might help you understand this video a bit more. Okay, so let's get on to how binary works. The basic way we explain binary is basically on and off states, because there's only two digits that we can use. For example, a light bulb, which has either an on state or an off state, or even if you're charging your laptop or not charging your laptop. As I talked about in the previous video, we have different number systems. We have the decimal system, which contains numbers from 0 through 9, and many more systems, of course. But all of these systems are pretty much the same, but the only thing different is how we represent them. For the decimal system, we had powers of 10, but now for binary, we're using powers of 2. So the labels for each placement would be 1, 2, 4, 8, 16, 32, 64, and so on and so forth. So for example, the number 15, how would we represent it in binary? Well, it's pretty simple if we use this model. All we have to do is put the 1 in the positions we need to make the sum of the numbers equal to 15 in this case. So in this case, we would need to put the 1s in the 8, 4, 2, and 1's position. So we can add up to make the number 15 as an answer. So basically 15 in binary is 1, 1, 1, 1. And we don't need the leading zeros because they're pretty insignificant in this case. Now let's try the same practice but for a larger number, like 312. In this case, because 312 is a bigger number, we need to add more numbers. So this one is also pretty simple. All we have to do is add a 1 in the 256, 32, 16, and 8's positions, which would add up and then give us 312. So each of these columns containing a number is called a bit, which basically stands for binary digit. Because one bit is not enough for representing information, because you only have either 1 or 0, we need a longer bit. And that brings us to a byte, which is just 8 bits beside each other to represent a larger number. And you may be wondering what part of our devices this operation happens in. Well, we have many tiny switches in our computers called transistors. But now using binary, so far we can only represent numbers. What about other types of information, like text, images, and others? So we need to find a way to represent characters and letters using the same system we use to represent numbers. But how? So basically, if we take the letter A by example, we would need to represent this using a number, so the computer or word processor can understand it and give us an output. So for example, the capital letter A is represented by the number 65. So if we were to represent the letter A in a byte, all we need to do is turn on the positions of 64 and 1. But again, we have more alphabets and symbols than just normal letters. So how do we represent those? Well, we can just use something called ASCII, the American Standard Code for Information Interchange. And what is ASCII? It is basically a map of all characters, letters, and symbols that we represent using digits. For example, here we have some of the letters in the alphabet and the represented ASCII codes. So let's say we have the letter H, which is 72, and then we have the letter I, which is represented by the digit 73. So for example, if you received a message from your friend to your computer and it said 72, 73, 33, that will mean that the person has sent you the word hi with an exclamation mark. But you don't see this operation happening. Only the computer does it and converts the digits and displays the letters HI in the exclamation mark. And of course we have other symbols and punctuations, which was not on that list, but 33 is basically the code for an exclamation mark. And it's crazy to think that all the letters and symbols on our keyboard have different digits behind them. But yet again, we have more things to represent, like letters with accents for other languages, and even these things. Yes, emojis. Although they just seem like images, they are on the keyboard, so they would need specific codes to represent them. And this leads us to Unicode, which is another specific patterns of 1s and 0s which represent these emojis and other symbols. But ASCII only uses 8 bits to represent symbols or letters, but Unicode uses anywhere from 8 bits to 32 bits, or even more. And we use these larger patterns of 0s and 1s to represent emojis like this laughing emoji. And the code used to represent this emoji is not 65 or 72. It's actually 128,514. And this is crazy because that means there are so many symbols, letters, and emojis for the number to drastically increase. Okay, thank you for watching this video. This was the second part for this computer science course. If you enjoyed this video, please feel free to subscribe and hit that bell icon. It makes you notified every time I upload. Thank you for watching, and bye bye.